All right. Well, good morning to everybody, or good evening. This is going to be the first day that we actually get into Agile Mind, which is our new curriculum. So today we're all going to learn how to access our actual content by going to webster.agilemind.com. So I'm going to show y'all how to do that in just a second. I'm going to present my screen. Lainey, are you in first hour or in fifth hour?
It just gave me a notification that I was in this class.
Okay. If you're normally in my first hour, you can just meet me in first hour. But if you do you have who do you have fifth hour?
I didn't get a schedule of who I was supposed to go to.
Oh, really? All right. So what I want you to do is go to your parent center and see if it will show you who shows up for your fifth hour teacher. Do you know how to get into parent center on J Campus?
No, sir.
Oh, all right. Well, you missed my class this morning, so as long as you don't get another invite, I'm sure it's cool that you can stay in here, okay? But I'm pretty sure you're my first hour. Does that sound good?
I was in your first hour.
You were this morning?
Yes, sir.
Yeah. All right. That's what I was thinking. You're in my first hour. But remember, first hour messed up. So if your other teacher doesn't have class right now and they don't call you, then you can stay in here if you want to, okay? All right. So I'm going to go ahead and I'm going to present my screen so I can show y'all how to go ahead and log in to your Agile Mind. So I'm going to do that now. So I'm still going to be able to see y'all. So make sure your screens are on. But I'm going to go ahead and present my screen. So it'll take just a couple minutes. Once my screen is presented, if you would give me a thumbs up, that'd be great. All right. Are y'all seeing the Agile Mind screen?
Yes, sir.
All right. Good deal. All right. So I'm going to show y'all how to log into this and make it very simple for you, okay? So what we're going to do, I want you to click on the top bar just like that. So you would go ahead and click your top bar. If you got something in there, you can backspace it out or you can use your cursor and pull this and then do it. But what you're going to do is you're going to type in Webster dot agilemind.com. All right, so whenever you do that, you're going to click enter, and then it's going to want you to put your username and log in. So I'm going to show you how it's going to work. So say for instance, we're all going to use our Google account, okay? So using our Google account, the only thing we're not going to use is the stu dot and the at websterpsb.org. So I'm going to give you an example of someone's name. I'm not going to say this works, but say for instance, we had Brody, middle name Louis, and normally it would be like dot. I'll put a last name Kevin at websterpsb.org. All right. So the way that our username is going to change is we're not going to use our STU. All right. And we're not going to use any periods. So we're going to take those out, and then we would take at websterpsb.org out. So it's just like your regular Google account, except you don't have any periods and you don't have STU or at websterpsb behind it. So if you understand what I'm saying about your username, can you please give me a thumbs up? All right. Your password is exactly the same. So for instance, this guy right here, since his first name is Brody and his last name's Kevin, it would be BK and then his numbers. So I'm going to say his numbers are 1, 2, 3, 4, 5, 6, and then I would click sign in. So that's how we're going to sign in. So does everybody understand that their password is exactly the same as your Google account? All right, we're going to keep moving. So I'm going to go ahead and log in. You're more than welcome to open you another screen and log into yours right now as you watch along with me, because you're going to be using this just as well as I am, okay? So I'm going to go ahead and log into this now, and then I'll show you how it's going to work for us. All right, so you notice it's going to show us tips right here. We don't need these tips right now. Basically what we have is we have our dashboard, our calendar, our courses, and our glossary, okay? Right now what we're going to do is we're going to click my courses, and you'll notice that it says assignment. So if you're logging into yours right now, what you would do is you would click the arrow on assignment. So I'm going to go to what we actually have right now. So what we have is our overview. So we're going to go over our overview, and we're going to do that together. And so we're going to start off by going over what our actual goal and objectives are for today. So our objective for block 1 is that we can apply proportional reasoning in a range of contexts, including scaling and mixtures. All right. So who in here can tell me what a ratio is? Can somebody tell me the definition of a ratio? Alora, what is a ratio?
A ratio is an association of two or more quantities.
Great job. All right. And so she was going to say a ratio statement describes how the quantities are related. All right. Why would a ratio be useful in everyday life? Does anybody got an idea yet? Or who can give me an example of a ratio? Let's
Like 2 to 4.
Good, 2 to 4. So for instance, if you're looking at this right here where we have our boys and our girls, what is the ratio of boys to girls?
2 to 3.
2 to 3. So what would the ratio of girls to boys be?
3 to 2.
Good job. Good job. All right, looking at this guy. He is creating some pizzas. So right now, it has 2 cups of flour to 1 cup of water. All right, or half a cup of water to 1 cup of flour. So if you have your book right now, what I want you to do, I want you to look at your first questions in your book. All right, so when you look at the first question, it says, what is the ratio of girls to boys in your class? So let's see if we can figure that out. I'm going to go through the names, and let's see, Akira, I want you to take down who the girls are, and Braden, I want you to take down who the boys are, okay?
Yes, sir.
And I'm going to see who we got. All right, so we have Akira, Alora, Asia, Braden, Brooklyn, Emma, Hagen, Kalia, Kyron, Laney, Levi, Natalia, and Rachel. So, Braden, how many boys do we have?
4 boys.
All right. And Akira, how many girls do we have?
10 girls.
All right. 10 girls and 4 boys. I think that's right. That looks good. So, with that, when it says what is the ratio of girls to boys in your class, what would that be?
10 to 4.
Good job, 10 to 4. So the ratio of girls to boys is 10 to 4. How could we write that? What are some ways that we could write that?
20 to 8.
Yeah, that would work if we were using the same. But what I mean by writing 10 to 4, I'm going to see if I can get our actual pen to work. If I can get this pen to work, I'll show you what I'm talking about. All right, so we could write it as just our regular old 10. Ooh, looks kind of ugly, but it'll work. So we have 10 to 4. Kind of slow with this. This mouse is pretty tough. All right, we got 10 to 4. What's another way we could do it? Could I write it out like in word form?
Yes, sir.
So
10
I,
girls to 4 boys.
yeah, I could write it like that. Or I can just put 10 and then 2, 4, right? My goodness, this is slow. It's all right. All right. Does anyone know another way we could do it? Could I put 10 as a denominator? I mean, not a denominator, but a numerator? Could I say 10 to 4 like this? Would that also be a way to write a ratio? Yeah, it is. It is. So, how many ways do we have to write a ratio? Say it, Akira.
3.
3 ways. That's right. So, there are 3 ways to write a ratio. All right. So, we had word form, and then we wrote it as a fraction, and we wrote it as a regular ratio, right? Does anybody have a question about that right now? All right. Well, we're going to wait. Kyron does. Kyron, what's your question, buddy?
I thought that we couldn't do the 10 over 4 because I thought the smaller number had to be on top.
All right. So we can do it. That is called an improper fraction. But since we're just writing a ratio, we can write it as a ratio that way. If we were working a problem, we just wouldn't leave it as 10 over 4 because, like you said, it's an improper fraction. So good job. Good eye. All right. So let's look at part B on number 1. Would you read that question for us, please, Levi? Help him out, Laney. Number 1, part B, starts with a jar contains blue. Go ahead, Braden.
A jar contains blue and red marbles. The ratio of red marbles to blue marbles is 4/2. Write three more equivalent fractions.
All right. So when we're creating equivalent ratios, what's the key thing to remember? How do we create equivalent ratios? What do we have to do
It
to?
has to be equivalent to each other.
They do have to be equivalent to each other. Kyron, what were you going to say?
Don't you usually add the number again?
Kind of. I think you're trying to say that we would multiply both parts of the ratio. Is that what you were trying to say? Good job, Kyron. Akira, what were you going to say?
I was going to say you have to multiply every ratio times 2.
Okay, you could do that. So, say for instance, we take this first one. We said it was 4-2, right? So if we have 4-2, what would we need to do in order to fill that out?
Multiply 4 times 2, then 2 times 4. That's what you could do.
Correct. So the blue marbles, instead of us having 2 blue marbles, how many blue marbles would we have?
4.
4. All right. How many red marbles would we have?
8.
Great job. So there's one. Somebody other than Braden give us another one. Also, while we're waiting on that, make sure that I can see your face. If your screen's turned off, make sure your screen is on.
Um, 6 and 16.
All right. So if we did, say for instance, we got 6 blue marbles, that would mean that we multiplied our first ratio by how much?
2. 4.
Think about it again. He said that the blue marbles is 6. So if the blue marbles is 6 and it was originally 2, what did we multiply it by?
Got 2. 3.
By 3. Because 2 times 3 would equal what?
6.
It would equal 6. All right. So that means that we need to multiply 4 by how much?
3.
By 3. So how many red marbles should we have?
12.
12. Good. So there's 2 more for y'all to complete in that table. I'm going to give you about 30 seconds to see if you can come up with those, and I'll ask and see if we can get some other answers. All right, Levi, what's one that you come up with? For
10, 20.
10 to 20 would work perfectly. All right. What about you, Miss Brooklyn? 8 to 16 would work also. Great job. All right. So let's look at part C. While ago, while we were on our overview and we were looking at the guy that flipped the pizza around, he flipped that pizza around and it told us how many cups of flour there were to cups of water. So I'm pulling that up real quick and I want us to look at that again and look and see what it says. And then we're going to fill out our work with it. So with those ratios, what is the ratio that it says? What are the 2 associated rates? What's one of them?
One of them are 2.
Okay. 2 to what? Can you read the actually associated unit rate? Like read the whole thing?
Is associated with 2 to 1.
It is 2 to 1. So we would say 2 cups of flour per 1 cup of what?
Water.
Of water. All right. So if we had a half a cup of water, what would it be to?
A half a cup of water per 1 cup of flour.
Perfect. All right. So that's what we should have for part C. All right. So now what we're going to do is we're going to figure out what scale factor is. So we're going to learn what a scale factor is. So since I don't know what scale factor is, I'm going to go to my glossary and I'm going to look up scale factor so I can figure out what that word actually means. So I'm going to go in here and search it. And so I've started and I got scale factor pulled up. And we're going to let Miss Emma tell us what a scale factor is. Emma, can you tell us what a scale factor is? Hagen, can you help her out?
The quotient of the measures of each corresponding size in two similar figures.
Great job. So a scale factor is going to be used whenever we do what? Emma, what's it going to be used for?
None of my
Talk loud.
none of my screen will load. Like I can't see you.
All right, can you see the screen that says scale factor on it?
Yes.
All right, so where it says a scale factor is used, what's it used for? Look right here.
To reduce or enlarge a figure.
There you go. Good job. All right, so let's talk about reducing or enlarging. If we reduce something, reduce means that we are going to shrink an item. All right, it's going to get smaller in size. If we enlarge something, it is going to get larger or it's going to grow in size. So, what does it mean to reduce something?
Shrinking size.
Good job. Brooklyn, in what does it mean to enlarge something?
Enlarge means to make something.
You cut out a little bit. Try it again.
Enlarge means to make something bigger.
Great job. All right. So does everybody understand that? If y'all understand what it means to enlarge or reduce something, would you give me a thumbs up? All right. If we need some help, does anybody need any help? Raise your hand if you still need some help understanding what it means to enlarge or reduce something. All right. We're going to keep moving. All right. So on number 2, on page 2, it says, what is a scale factor? So in our workbook, we should have put a scale factor is a number that you can multiply the dimensions of a figure by to enlarge or reduce a figure without distorting. All right. Or you could have wrote exactly what we just said. A scale factor is the quotient of the measures of each pair of corresponding sides in two similar figures. All right. So the main thing to notice there is that a scale factor is the number that we multiply a ratio by in order to either enlarge it or reduce it. So what's important here is when we have a scale factor that is less than 1, that is going to reduce. If we have a scale factor that is larger than 1, it is going to enlarge. All right? So we're going to see how that works in just a second. So I'm going to go back to our actual course, and we're going to look at our next page on page 2. So notice I'm going up here and clicking the 3 dots, and I'm clicking my page as page 2. All right, so we're going to look at this, and we're going to read this. So if you would, Levi, would you read this for us?
The top one where it says to change.
Yes, sir.
To change the size of a photo without distorting it, you need to reason with ratios. This type of reasoning is called proportional reasoning. Because the dimensions must be changed proportionally, in other words, the ratios of the corresponding dimensions must be equivalent. Use the animation to explore.
All right, so if you look at it, it says, what if you want to change the size of this photo, but make the photo look the same? So if we want the photo to look the same, we're going to have to enlarge it both in length and width, because if we don't, it will make it look funny, okay? So I'm going to get it to go through and show us how this is going to work. So if we look at this, the original length was 4.5 and the width was 2. All right? But if we wanted to increase this twice the size or have a scale factor of 2, what happens to the new image? How big is it now?
9 by 4.
That's right. It's 9 by 4. So if we have a scale factor of 3, look what happens. So now it's 13.5 to 6. So every time, what's taking place?
It's getting larger.
It is getting larger. So that means we have an enlargement. And you also should notice that the length and the width are both being multiplied by what?
2.
Yeah, it was multiplied by 2 at first, then 3, then 4, then 5. So in each case, the length and the width are both being multiplied by the what? They're being multiplied by the same number. All right, that's what allows it to grow. All right, in this case, each number is greater than 1, so we're enlarging. If these numbers were less than 1, such as 3/4, 1/2, 1/5, it would make it do what? Would it enlarge or would it what?
Shrink.
It would shrink. It would reduce. Good job. So let's look at number 2. So what's taking place here? That's right. It's reducing. So notice right there, it said 3/4, and then the second one was 1/4. So 1/4 is our what in this case? It's the word we just talked about. We just took the definition.
Our factor scale?
Yeah, our scale factor. That's right. So right here, it says the ratios of length to width in the table are equivalent. The number by which you multiply each length and width to get the dimensions of another image is called the scale factor. Can everybody see that?
Yes, sir.
All right. What's it say right after that? It says if you multiply both by what?
1/4.
All right. If we multiply them both by 1/4, what happens?
It reduces.
That's right. It's reducing. It's getting smaller in size. All right. So let's continue. We're going to go on to page 3. Look at this. It says, in this case, the images do not look the same. They're distorted. So what do you notice about that second picture right there that says 5 to 8? What's happening to her? Does she look the same?
No, sir.
No, she doesn't look the same at all. She looks what? Did she get fatter or wider? I don't know. Isn't she getting thicker?
Yes, sir.
All right. And then on the other one, on that far right, she's not getting wider. What's she getting?
Skinnier.
She's getting skinnier and really tall, right? So
Yes, sir.
do y'all see the difference in a proportional image and a distorted image?
Yes, sir.
So a proportional image is either going to enlarge or reduce, and a distorted image, is it going to look right?
No, sir.
No, it's not. No, it's not. So look right there at the bottom. What does it say, Kalia, in the yellow?
These images have been scaled.
Do you see where it says notice there's not at the very bottom?
No, because this thing is over. Okay, there you go.
You got it fixed up?
Notice there's not a single factor by which you can multiply both dimensions to get another pair of dimensions. The ratios in the table are not equivalent. These images have not been scaled proportionally.
All right. So when we say proportionally, that means that they have a what? Or that means what's happening to both parts of the ratio?
They're enlarging.
Yes, or we could say that both parts of the ratio are being multiplied by the same number. Does that make sense? That's what gives us a proportional relationship, okay? All right, let's keep moving. We're going to move to page 3. All right, so let's look at this. It says ratios and rates can also be useful in describing mixtures. We're going to play the animation to apply ratios and rates to paint mixtures. So it says you can use proportional reasoning to mix paint and create new colors. So when you mix one part of yellow to one part of blue, we're creating a green. So notice right here we've got 4 cups of blue to 4 cups of yellow, and it gave us a 1-to-1 mixture of green. What do you think would happen if we used 4 cups of blue and 4 cups of yellow? Would that be a proportional mixture?
No, sir.
No. So what do you think is going to happen to the color? Would it get darker or lighter?
Darker.
All right, let's see. So we got 4 cups of blue, and we're going to do 8 cups of yellow. So let's see if it gets darker or lighter. So what did we notice?
It got lighter.
It got lighter.
Yeah, it got lighter. So the ratios in the table are not equivalent. So what would happen if we were to use more blue than yellow?
It will get darker.
It will get darker.
Yeah, it would get darker. All right, does anybody have a question about this slide here?
No, sir.
All right, we're going to keep moving. Let's go to page 4. All right, if you would, Miss Rachel, will you read that, please?
You have seen that ratios, rates, and proportional reasoning are important when you mix paint colors and resize images. But there are many other uses for proportional reasoning. Play the animation to see some of them.
All right, so let's see what happens in the distance in miles and the time in hours when we travel. What's happening as we travel in miles?
Our time is getting larger.
That's right. So the further we go, the more what is spent?
Time.
That's right. So what does it say down there in yellow, Akira?
You can use proportional reasonings to figure out how long it will take you to get to your destination. You can also use ratios and rates to find distance matters.
All right. So let's go ahead and let's take a look at part 2 of this. Here it goes. I had a pop-up come in front of it. All right, so if you look right here, it says, when you want to feed more people than a recipe calls for, you must increase the quantities in the recipe for the taste to stay the same. So each ingredient must be increased proportionally. So what happens if we don't increase it proportionally? Is it going to taste the same?
No, sir.
No. All right, so let's look at what happens here. So they're going from 1 quart to 4 quarts of ice cream. So what does that mean is going to happen to each part in the recipe? What's happening to each part in the recipe?
They're adding more of it.
All right, it is getting added more. By how many times is it being multiplied by?
2.
Well, we started off with 2 egg yolks, and now there's 8. So what did we multiply by?
Multiply by 4.
That's right. So every part of that recipe was multiplied by 4 so that we would have 4 quarts of ice cream instead of 1 quart. So our scale factor for this would be what? Another meaning for the scale factor would be, what number did we multiply each part of the recipe by?
4.
4. So the scale factor is what?
4.
Great job. All right, let's look at page 5. All right, so let's look at this. One of the questions it says is, how do chefs change recipes? So, Asia, do you know how a chef changes a recipe? What do they do to a recipe if the recipe is normally for one person, but 10 people come in to eat the same thing? What do they have to do to that recipe? What do you think, Asia? Help her out, Lainey. All right, so it's originally the recipe is for one person, but the chef needs to make it for 10 people. So if he wants the recipe to taste the same, what would he have to do since it's going to be for 10 people instead of one person?
Double it.
All right, if he doubles it, that's going to make it for how many people? If it was originally for one, if we double it, how many would it make it for?
2.
It'd make it for 2. So what do we need to do to make it so that it'll be for 10 people?
So 10.
Yeah, we'd have a scale factor of 10. So in this case, would it enlarge or would it reduce?
Enlarged.
Yeah, it would be enlarged. All right, this next question says, how do architects create scale drawings? So if you look at this little drawing on the right side, on the bottom right side, you'll notice that we got basically a part of the house. We got a living room, a bedroom, another bedroom, and a bathroom. And so each one of these is measured in centimeters. But are houses in centimeters? No, they're not. What are they normally in?
Square feet.
Yeah, in square feet. So in this case, what does it say 1 centimeter is equal to?
2 square feet.
2 square feet. That's correct, or 2 feet. So since it's that means for every centimeter they draw on that paper, that represents how much?
2 square feet.
2 square feet. So how big would one of those bedrooms be? What would be the length and width of that bedroom?
6.5. 6.5.
The bedroom?
11.
All right. So how'd you get that?
I multiplied 5 times 5 to 2.
That's right. Does that make sense?
I meant 5.5.
I knew what you meant. Did that make sense, Akira? All right. So he did 5.5 times 2. So when we did that, he got 11. All right? Because 0.5 times 2 is 1, and 5 times 2 is 10. And 10 plus 1 is what?
11.
Great job. All right. So it says, how do we correctly read maps? So most of us, when we see maps, they're normally on like navigation consoles or on our phone, when we look at our phone, you notice that it has a Google Maps. But before we had all of that, we had actual maps. And so when we had our maps, they were broken down the same way. They would have a scale like this. So 1 centimeter might actually be 100 miles. So when reading a map, you would have to find the scale to determine how many centimeters was equal to a mile, so you knew how far you had traveled. So that's how we would correctly read a map. All right, so it's important that we know that in this topic, we're basically realizing that proportional reasoning is the key. We're going to learn to use proportional reasoning, and we're going to use it over and over again. All right, and so using that, I want everybody to look at number 3 in their workbook. So when we look at number 3, what does it say? Number 3 in our workbook.
Situations in which you might use proportional reasoning.
All right. So let's get one. I still haven't heard from Asia today. Asia, I need you to give me one way in which we would use proportional reasoning. Hagen, I want to know a way. Kalia. And Kyron. Everybody else be thinking of a way also, because I could call on you at any moment.
Maybe like if you order one pizza and how pizzas have 8 slices and 10 people come over instead of the amount of people instead of 8 people, 10 people come over.
All right, so let's say this. So since 10 people came over, is one pizza going to be enough?
No, sir.
No. So if one pizza has 8 pieces of pizza, how many would 2 pieces of pizza have?
16.
Great job. So we could say ordering pizza or ordering food, that we could use proportional reasoning. So we would know that we needed to have more pizza so that we'd have enough and everybody could get full, right?
Yes, sir.
Great example, man. All right, we're still waiting on our others. Miss Asia, waiting on you. What's a way we could use proportional reasoning? What's something we use today in class?
One way you can use proportional reason is like when you have people come over and you have candy, but you don't have enough to share with everyone.
All right, you said so whenever, like if we needed to get candy for everyone? Is that what you were saying? You kind of cut out at the end. Can y'all hear her, guys? I can't hear you, Asia. I'm sorry. I think what you were saying is that we had enough candy. Say so, for instance, I'm going to kind of go off of what you just said. If one package of candy has 5 pieces in it, but we have 15 people coming over and we want to give candy to every person, how many packages of candy would we need to buy? Show me with your fingers. Or you can type it in the chat box. So if one has 5 pieces of candy and we got 15 people that we want to give candy to, how many packages would we need? Great job. 3 packages. That's perfect. All right. We were also waiting on 2 more people. We were waiting on Mr. Hagan. Hagan, what do you got? Say it again, Hagan.
I said if you make a pitcher of lemonade for 5 people, but then 10 people come, you won't have enough lemonade.
All right, so what would we have to do?
Get another pitcher of lemonade.
Okay, good job. Good job. All right. Oh, there was something else that we did. What else did we do today? We were waiting on one more person. I don't guess they're gonna participate with us. Who else can tell us something else that we did today in class? Go ahead, Braden.
About proportional reasoning.
Yes, sir.
Reasoning.
Mm-hmm.
Something that we did in class or something that I made up.
Your choice.
Okay, so I'll just do something we did in class. So the chef. All right, so I'm gonna do the chef. The chef was prepared to cook for 1 person, but 10 people came, so he had to cook enough for 10 people.
All right, that's a good example. What about we also mix paint in class, right? So if we say, for instance, earlier we had 4 parts of blue to 4 parts of yellow to make green. And in total, that's 8 parts, right? Well, what if I only needed a total of 4 parts of paint? How much blue would there be to how much yellow?
You would need 2 blue paints and 2 yellow paints.
Great job. That's perfect. Perfect job. So that is proportional reasoning. Y'all did a great job today. All right. So if you'll notice, we have questions 4, 5, and 6. 4, 5, and 6, we're actually going to try to work on our own, and I'm going to give y'all a little time to do that. But before we can work problems 4, 5, and 6, we got to answer a couple of problems so that we can be able to do that. So I want to take a poll of how many left-handed students there are. So if you are left-handed, I would like you to speak up now.
I am.
All right. So far, we got 2 people that are left-handed. Is that what I saw? Does that sound right? I got Kyron and
I'm
Rachel.
left-handed.
Who said I'm left-handed? I think we got 2. Yeah. So we got Kyron and Rachel are both left-handed. And so we got a total of 14 more people, or 14 people in all. So how many people would be right-handed if 2 people are left-handed? Good job. Good job. All right. So we got 12 right-handed students and we have 2 left-handed students. All right. So we're going to answer questions A and B and C off of that. All right. We're also going to need to know how many inches are in a foot. How many inches are in a foot? Hagen, how many inches are in a foot? 12 inches are in a foot. Good job. How many centimeters are in a meter? Who knows how many centimeters are in a meter?
$100.
Great job. There are 100 centimeters in 1 meter. And how many feet are in 1 yard?
3.
Great job. There are 3 feet in 1 yard. And then on problem number 6, we don't need any information because they've given us all the information. So right now, what I want you to do is I want you to answer problems 4, 5, and 6, parts A, B, and C. And that's actually going to be the ending of our classwork. So I'm going to give you time to do that now, and then we'll review over those here in just a few minutes, okay? So I'm going to go ahead and quit recording our lesson, and then I'm going to let y'all work on that now by yourselves. And then in about, I don't know, maybe
What questions did you say again?
we're going to do 4, 5, and 6 in our workbook. Parts A, B, and C on each one.
All right.
And I'm going to give y'all a few minutes to do that.